Good morning, Chemistry 20s. Our lesson today is going to be on acid-base indicators. An indicator is a substance that changes color in solution when the acidity of the solution changes. It can have at least two forms. We have previously looked at litmus paper, when it's changing, right, red and blue to signify acids or bases. In Science 10, we did a lab where we used a natural indicator, cabbage juice. We took purple cabbage, we put it in water, we boiled it for a few minutes, and we collected the purple cabbage water. When we then take that purple cabbage water and we put it in something neutral, this is where it turns kind of a bluish color. If we were to take purple cabbage water and we were to drop it into a strong acid, it would turn red. And if we were to take purple cabbage water and drop it into a strong base, it would turn yellow. It's a natural indicator. Two other indicators that we used in Science 10 are called bromothymol blue and phenolphthalein, and we're going to take a closer look at them on the next few slides. At this time, I would have you find your chemistry data booklet and flip to page 10. There is a list of acid-base indicators on that chart, and I'm going to teach you how to read the chart. So if I take a look at bromothymol blue, you will see that bromothymol blue, we said in the previous slide, like all indicators, has two forms that we write. HBB is the acid form of bromothymol blue. BB minus is the base form of bromothymol blue. The difference between the two is the one proton, right? Kind of like HCl has a proton that makes it the acid form. If I donate the proton and I'm left with Cl minus, or in our case, Bb minus, that is a base form. And we'll look closer to that in future slides. When we're reading this chart, you will see that bromothymol blue has a pH range from 6 to 7.6, and that the color changes from yellow to blue as the pH increases. This means that from 6.0 and below, the color is going to be yellow. So if I was to put bromothymol blue into a solution that had a pH of 6.0, 4.0, 2.5, or 1.1, they would all be yellow. All the solution would turn yellow with bromothymol blue. If we had a solution of 7.6 or greater, and I dropped in bromothymol blue, then we would notice that it would turn blue. So whether I have a pH of 14, 10, 9, or 7.6, my solution would turn blue. Any pH value between 6.0 and 7.6, not including those two values, that would then be the middle color between yellow and blue. And I hope we realize that that middle color is then green. Before we go on, I want to talk about this, right? So we got to know our, what I like to call our elementary school secondary colors. So yellow, blue, middle is going to be green. Red, blue, middle is going to be purple. Red, yellow, middle is going to be orange. Now, there is a few others that are going to be a little bit different, but you're going to see that they're actually quite straightforward as we go. So how do I write out these pHs? Well, when I have a pH of 6.0 or less, right? So we're going this way, or less, it's going to be yellow. So I write it like this. When I have a pH of less than or equal to 6.0, that's when it's going to be yellow. And what we can do is, we'll get rid of my pen for a second and we'll get the colors on here. So anything 6.0, including 6.0 and less, is yellow. So pH less than equal to 6.0. Again, let's do blue because it's the next easiest. So anytime the pH is greater than or equal to 7.6, it's going to be blue. And then the middle range is the tough one because it doesn't include 6.0. Green does not include 7.6. It's going to be between 6.0 and 7.6. So the way I always do it is always read from the pH sign. So when the pH is less than 7.6, it is going to be green. Again, read from the pH sign. When the pH is greater than 6.0, it's also going to be green. So when the pH is greater than 6.0, or when the pH is less than 7.6, so both of these criterias, that's when we're going to get the green color. Now, I'm trying to figure out, well, why sometimes is this indicator yellow? Why is it blue? Why is it green? Why does this actually happen? What is actually happening in these scenarios? And what's happening in these scenarios is that when it's yellow, this is when my bromothymol blue is in its acid form. It has not donated any protons yet, therefore it's going to show up in the solution as yellow. On the other extreme, when the solution, my indicator has donated a proton already, it's in its base form, and right, that's when it's going to be blue. These are the two forms of indicator: acid form, base form. Now, in between here, this is the special case. When you're in between the acid form and the base form, this is where it changes form. This is where we have a difference of one proton. This is where that proton is moving. It's actually very, very hard to get this middle form because it might not even take a full drop. This might take half a drop or a quarter of a drop. We saw this when we were doing titrations, right? Where we're going along, we're doing our titrations, and all of a sudden, instantaneous, there's a one drop color change. And sometimes it went straight from yellow to blue. There was no middle ground. Because remember, I can't drop a quarter of a drop. So sometimes it's just, ooh, right away to blue. We are trying to get the green in the titration, but sometimes it doesn't take a full drop. Now, if we were back here and we added a drop, maybe we would land in this pH range, and then we would see it green, and we would know, okay, we're going to stop now. We have done the one drop color change, and we're good to go. Well, let's try a new example. So I have phenolphthalein. Again, something we've also used in Science 10. If you look it up, our pH range is from 8.2 to 10.0. So that's from colorless to pink. And so down here from 8.2 and below, including 8.2, it's going to be colorless. From 10.0 and above, including 10.0, it's going to be pink. And you have to ask yourself, what is the color between colorless and pink? And I always call it just light pink. We don't have to reinvent the color wheel here. We don't have to make it difficult. Um, there's no purpose to that. So what I want to do is let's write down the ranges again when we go to do this. So when is the pH colorless in phenolphthalein? It's colorless when the pH is less than and equal to 8.2. When is the pH pink? Well, it's pink when the pH is greater than and equal to 10.0. And then this small range in here where it's light pink, that is when the pH is less than 10. And we're going to read from the pH sign. And we're going to read from the pH sign again. Not only is it less than 10, it's also greater than 8.2. So we are reading from the pH sign across and the pH sign across. Now, I'm going to get my pointer tool out here. So again, when I'm down here, this is my acid form of my indicator. This would be the HPH range. When I'm above the change in color, this is going to be my base form. This is my pH minus. And when I'm in between my pH range, this is when I'm looking at a one drop color change. And oh my goodness, we have a typo. Mr. Kemp wasn't careful. So this is HPH and pH minus on there. So I apologize for that. Okay. What I would like you to do is, why don't you copy example 1 and 2, pause the video, confer with your indicator chart, write out your pH range, and then unpause the video to check your work. So in example 1, a solution is tested with methyl violet indicator, and the solution turns blue. What range is the pH of this solution? So I'm going to check my data booklet on page 10. It's the first indicator listed, and it says it is 0.0 to 1.6 or yellow to blue. Therefore, it turns blue when the pH is greater than or equal to 1.6. Let's look at example number 2. A solution is tested with thymal blue, and the indicator turns green. What is the pH range of this solution? Now, thymal blue, you'll notice there's a few on your table, but thymal blue is one of them that actually changes colors twice. So with the same indicator, it can indicate how acidic something is because it's got a very low pH value, but can also indicate how basic something is because it has a weak base sort of range there. So it actually changes color twice. So when is it green? Well, it is green when the pH is less than 9.6, but the pH is greater than 8.0. Beautiful. And by the way, when I go to mark this, you would get 1 mark for writing this. Down here, I would make this out of 2 marks. You get a mark for telling me pH is less than 9.6, not including 9.6, and pH is greater than 8.0, not including 8.0. So this one's a little bit tougher. You'd get more marks for it. Now, has been easy so far. However, in some problems, the color of several different indicators will be listed. We will use all the indicators as little clues to narrow down the pH range, and then we will choose the middle of the pH range to determine the hydronium ion concentration. So when I did this in class, I always tell my students, think of it like you're a mini detective. Pick your favorite detective. Sherlock Holmes, Nancy Drew, Scooby Doo. It honestly doesn't matter to me. And what we're going to do is we're going to use these clues from different indicators, and we are going to collect these little tiny clues. So I have a solution. Think of it as a beaker, and I don't know its pH. So I'm going to take this and I'm going to pour a little bit into smaller beakers. And in the first beaker, I'm going to add orange 4. In the second beaker, I'm going to add some chlorophenol red. And in the third beaker, I'm going to add bromocresol green. And they've all changed colors. And we're going to use these clues to try to figure out what is my pH range of this mystery solution. So I'm going to find orange 4. And orange 4 is yellow when the pH is greater than or equal to 2.8. Chlorophenol is yellow when the pH is less than or equal to 5.2. And then bromocresol green is green when the pH is less than 5.4 and the pH is greater than 3.8. So we have collected all of our little clues. Now, what I would like to do is let's add all these clues together. So let's take one clue at a time. We're going to put it on here and we're going to see what it tells us. So using clue number 1, we know that in this, because orange 4 turned yellow, we know that the pH is greater than or equal to 2.8. So pH is greater than or equal to 2.8. You'll notice that I flipped my sign up above here, but remember, we always read from the pH sign. So I'm reading it from right to left this time. pH is greater than or equal to 2.8. We also know, so that's clue number 1. We also know that pH is less than or equal to 5.2. So it's greater than 2.8 or equal to 2.8, but it's also less than or equal to 5.2. So we've used our second clue. Third clue, our pH is less than 5.4. Well, we know it's less than 5.4 because we already know from clue 2 that it's less than or equal to 5.2. So if it's less than 5.2, of course it'll be less than 5.4. So this didn't give us any extra information, so we're just going to put a check mark and go thank you. And then last but not least, pH is greater than 3.8. Well, we currently know that the pH is greater than 2.8, but this is going to tighten our pH a little bit better. So not only is it greater than 2.8, it's actually more specifically greater than 3.8. So I'm going to just tweak this a little bit. So it's not greater than or equal to 2.8 anymore. It's actually pH is greater than 3.8. So I use that clue. My pH is greater than 3.8 and less than or equal to 5.2. So ideally, I would give you 2 marks for this question because you would get 1 mark for telling me it's greater than 3.8, and you get another mark for telling me it's less than or equal to 5.2. My follow-up question is for 1 mark. Is this solution acidic, basic, or neutral? Well, the pH is somewhere between 3.8 and 5.2. So of course then, this solution is acidic because pH is less than 7. And then we have to figure out the approximate hydronium ion concentration. And the reason I say approximate is because, right, our pH could be anywhere in between this, but we're going to get significantly different numbers if Mr. Kemp chooses, let's say, 3.9 and Mr. Van Leeuwen chooses 5.0. So we are going to find the middle. So you want to add 3.8 plus 5.2 and divide your number by 2. And what you're going to find is when you do that, you get a value of 4.5. So to find hydronium ion concentration, we have the formula. Hydronium ion concentration equals 10 to the negative pH. So we're going to do 10 to the negative 4.5. And I'm going to type this into my calculator. Again, my answer, and again, when I look 1 decimal place, by the way, they're all going to be 1 decimal place because when you look in your data booklet, all the pHs are listed as 1 decimal place. So that means I get 1 total significant digit. So when I type this in, 10 to the exponent negative 4.5, I'm going to get 3 times 10 to the negative 5 moles per liter concentration. Again, I would do this out of 2 marks, 1 for formula and substitution, 1 for answer with correct sig digs in units. So this question is out of 5. Please pause the video and I want you to collect your own data here, take your clues, add them together, and answer the following question. So phenolphthalein, when is it colorless? It's colorless when the pH is less than or equal to 8.2. Thymal blue is yellow. Oh, there's a range here. Thymal blue is yellow when the pH is less than and equal to 8.0. And thymal blue is also yellow when the pH is greater than or equal to 2.8. So quite a range there for yellow. And then chlorophenol red is red when the pH is greater than or equal to 6.8. So those are all my clues. We don't get any marks for that. Now we're going to add all this information together. So what is my pH range? So let's add the clues up. Well, we know the pH is less than or equal to 8.2. So thank you for that piece of information. We know the pH is less than or equal to 8. Well, so we're at 8.2. We're going to narrow it a little bit more. So now we know this is 8. So I'm going to do this for now, 8. So thank you, less than or equal to. We know the pH is greater than or equal to 2.8. So pH is greater than or equal to 2.8. And our last piece of information, our pH is greater than or equal to 6.8. So our pH is greater. So instead of 2.8, we're going to take a big jump. And this guy is actually 6.8. So let's clean that up a little bit because I made a mess. So we know that it's 6.8 and 8.0. 6.8 and 8.0. There we go. So pH is greater than or equal to 6.8. pH is less than or equal to 8.0. So we're going to give this out of 2. What is the hydronium ion concentration? So we have to find the middle between this, and that would be, looks to me like it's 7.4. So hydronium ion concentration equals 10 to the negative pH equals 10 to the negative 7.4. And so I type that in, 4 times 10 to the negative 8 moles per liter. If we take a look here, if I asked you, is this an acid, base, or neutral? I think we would say it could be all three. It could have a pH of 6.8 or 6.9, which would be an acid, could have a pH of 7, which is neutral, and it could be anything up to 8 and including 8, so it could be a base. So this test didn't really tell us a whole lot. Again, it's going to be out of 2. Well, the question is always, before we finish off, why do we care about indicators? Well, I've already referred to we use them to so we know when to stop doing a titration, but there's also things out there that we have that use indicators. And this might be those magic markers behind the magic behind color change markers, where I color something and then I take their magic marker, usually the white one, and I color over it. And where I've covered over it, it changes color or it deletes color. What we have found is that Crayola or these companies, they have all their markers. Let's say that they are slightly acidic. When you take the white marker, if it's slightly basic and I come over them and they have some indicators in them, that will change their colors. So on the paper, we get all these really cool multiple color changes for children's drawing tools.